Hello, everyone, and welcome to the online open We CAD Do It 10 video series. Now, whether you're barely being introduced to computer-aided design or you have a greater aptitude than even I do, hopefully this can A, serve to introduce people to the event and how it's going to function in May, as well as hopefully give people who have computer science and computer-aided design expertise, or maybe don't have that expertise, a greater leg in on what the things that the competition might entail are, as well as just cluing you into what is good to know for general CAD use in a professional and both fun environment. So let's get started. So what is We CAD Do It? Well, We CAD Do It is an event that's run by the Online Open where you are required to design a rim for a car. As you can see, that little Lego figure there is installing rims for that race car. And so this is obviously important for anyone who's ridden a car because you want to have something that can support the load of the axle, which is then supporting the load of your entire car. So we're going to teach you not only the skills that you'll need to design anything in CAD, but of course those that can be used to design something that can support a particular load, as well as support the forces that are acting on it in a natural environment. So, and we're going to use a different variety of programs to do that. You might find that there are features within CAD software, as well as those that are provided by other software that we might include that are going to be very important. So let's move forward. So what is computer-aided design? So computer-aided design usually takes 2 and 3D elements. You might have presets in 3D, or you might create your own 2D things that you extrude, which is basically to make 3D. And you use those things to construct pretty much anything you want. And it's really good to have this creative environment online because it costs a lot of money, as you would imagine, to create prototypes of very expensive things. And it would be very advantageous to create something like a car or to create the axle or wheel for a car in computer-aided design environments first and testing their structural integrity of the particular materials they're made of in computer-aided design before you'd actually go forward and test them in a real design environment. Because having to create the same car about 20 times is a lot less cost effective than creating it in CAD, iterating through different variations of testing online, and then creating it maybe 2 or 3 times before you go to market or before you pitch it to a professional. So computer-aided design is very useful for both hobbyists like myself who like to make fun things like little robots from 3D printed parts, or for people who are working with actual metal like the MIT rocket team, or like maybe Science Olympiad teams, or by professional companies who are developing cars, who are developing rocketry, who are developing aeronautical technologies. So there are different kinds of CAD software that exist out there. Some of them may vary in terms of the professionality. Things like SolidWorks might be limited to teams that work in competitions, or might be limited to even professionals because they might carry a higher price tag and have a lot more advanced features. Or there might be then some that differ in the kinds of jobs that they can do, the kinds of analysis that you might need. So for example, SolidWorks again is very good for professional analysis in electrical. That may be something that you will need. Or something like Autodesk Fusion 360 is good for teams that might need to exchange parts in between one another. And finally, there's also the front end differentiation. So as you can see on the right there, that's OpenSCAD. OpenSCAD is a lot different than other CAD design softwares. And the reason is that if you see on that left little window there, you can see that you're inputting actually a function. So you're programming based on the features that you want a shape or a figure to have. So I might create a circle, for example, that has a radius of 2.5 inches and then is extruded upwards. So that means a thickness for a cylinder of a certain amount. And it might have an X and Y coordinate that correspond to where the center might be, as opposed to other CAD design software like Fusion 360, SolidWorks, etc., AutoCAD might have a different form of presenting that data. So the way you do it, what you use it for, as well as the price tag that it carries with the amount of features that it has, are all important to computer-aided design. So what are you going to learn in this lecture series? Well, let's get started because there is a lot of content to cover. So the best thing I can do for you is sort of give you a sort of roadmap that we can start on. So first thing along our road of CAD magic is how to use it to begin with, how to use the very elementary features of sketch software. So sketch is where you would create something in two-dimensional CAD first. So that would be something like creating a spline, creating a circle, using a line tool, using an oval tool, text tool, creating planes, how to use planes, how things work in three-dimensional space, and how you might want to create sketches from faces of 3D objects. All of that would be covered, as well as how to use things in a three-dimensional design environment. So how would you use a negative extrude feature to cut holes? How would you use a hole feature to create holes that are tapered for bolts? You might have to, of course, extrude, which is bring into 3D, things that you have created in 2D. You might have a circle and turn that into a cylinder. All of that would be covered, as well as things like fillets, which is how to not make sharp edges not sharp, or maybe chamfers, which are more or less do the same thing, except instead of rounding edges, they would just completely null out that feature and create a 45-degree angle. So all that would be covered in a parametric CAD environment. So what is a parametric CAD environment? A parametric CAD environment is one where you would determine the features in terms of length, width, and have constraints on them. So a constraint-oriented environment, as you can see on that right image there, would have dimensions to it. So you might create a circle that is X inches long at this specific location and is extruded into a casket of X dimension or Y dimension tall. And that would be very important because there's also non-parametric CAD software, like AutoCAD is a good example, that doesn't necessarily use that approach. And in that case, is a lot more useful in 3D and blueprinting than it would be to model three-dimensional structures like a tire. So the next thing that you would want to learn are assembly and drafting and drawing file types. So both of these images seem to be pulled from SolidWorks. Now, we're not necessarily going to work in SolidWorks. The next session we'll find out which CAD software we'll be using. But there are different file types that you use for different purposes. So you might create a part or a unit file that essentially has that 3D object that you've created in it, but you might import that into a larger file called an assembly file where you would put all of this stuff together. And that would be very useful for, of course, taking different parts of a car, of a rocket, of another vehicle, of even anything like I have my suitcase sitting next to me. All of those things aren't just made of one continuous shape. They obviously have very many different components. They have wheels, they have axles, they have zippers, they have all of these different features, not necessarily made of the same material as well, because you'd also want separate features to have separate materials that construct them. So it would be important to have an assembly where you can bring different things together to create one whole, and that would make for a lot more efficient workings than to work on one specific file, because that would be very chaotic. As well as a drawing file. Drawing files can be used to represent things, as you can see on the right there, a lot more cleanly and with a lot less having to maneuver around. Because if you look on the left there, even though that part seems to be broken up into its individual components, it'd still be a bit difficult to understand how dimensions between them work. As you can see in the drawing file, it's no problem. They give you 3 different views, as well as an isometric view, which we'll talk about in a future presentation, that can break down all the dimensions and angles that have to do with constructing the figure. And a lot of times, you might even be given a drawing in a competition, and you'll be asked to construct the object based on that drawing. And you should be able to. That's the point of a drawing, to give you all the information you need to construct that object. So next, you'd be learning about not assembly and drafting file types, excuse me for mislabeling that there, but you'd learn how to do final analysis and calculations for that. So as you can see here, you have a multicolored scheme here on these objects. And what this would basically show is the amount of stress that is being placed on these items. So the amount of force per unit area that is being impacted by something that might happen. So for example, over here on the left, you see that you have these 3 arrows that are pushing down on this beam that's attached to the surface right here. And that surface has a very strong red area, which is where you're receiving the most amount of that stress. So you're seeing the greatest amount of tension placed there, which is, obviously the breaking point. So if I were to take a rod attached to a wall and press down on the end of that rod, It's not going to break at the tip, but rather at that conjoined point. And fine element analysis can show that. Fine element analysis is going to have you breaking a component up into different parts and seeing how a force might impact those parts individually. And that information gives you how the behaviors of that object would come together as a whole. And that will really help you justify why you wouldn't necessarily see something cleaving about halfway through, but rather close to the fulcrum here. And you can see as well those sorts of forces acting on the rim there. Not necessarily sure where the forces are on that. They're not really displayed. But you can see where the areas of highest pressure are applied. Where I'm using pressure very loosely, that's not necessarily the definition of pressure in a physical environment, but rather where you're receiving the most amount of, I'm going to break, as opposed to the least amount of, I'm going to break. And so that's very evident in the form of deformation on these different objects. Obviously, that blue area there on the rim is not supposed to be doing that whatsoever. And that rod attached to the wall is not supposed to be bending like that either. And we can use that to see how different materials will interact on an object that we create in computer-aided design. So that's basically our rundown. We'll be covering all of these topics and more in future presentations. I hope that this little intro gives you an idea of what we want to tackle and sort of has you excited for the future. And whether you're here to further your knowledge of computer-aided design, to prepare for this competition, or any other purpose, I hope that we can all have a whole lot of fun here and make this a great lecture series for everyone. So yeah, see everyone soon.